Welcome everyone to our tutorial. Good afternoon. It's a tutorial on uplift modeling from causal inference to personalization. Yeah, please take a seat. Before I start this tutorial, there is a website for this tutorial. If you haven't seen on the conference website, it's going to be there. You have there the slides, the recordings later on after this presentation, the reference that we use along this presentation, but also our context in case you want to reach out to us. I'm Felipe. Here with me, we have Hugo on the back, Anastasia. We both are machine learning science at booking.com. We are from Amsterdam. And just starting with me, I'm Felipe. I've been working at Booking for about 2 years now. Before Booking, I was a PhD student at Delft University of Technology in Information Retrieval. Why we're here? We are from Booking, and as maybe some of you don't know, Booking one of the leaders in travel company in many markets, including in Europe. We have more than 100 million monthly active app users. We are more in 70 countries. We have 5,000 employees in Amsterdam, but also have employees in UK, in Manchester, in London. But more specific, I want to talk about our machine learning. And we, as machine learning science, we are responsible about more than 350 models that we have in production. We are more than 800 machine learning practitioners. These include machine learning scientists, engineers, product managers, machine learning managers in the company. And we serve more than 200 billion predictions per day. With this experience, we hope that we can teach you about causal inference, but also uplift modeling. What are the learning goals of this tutorial? First, we're going to learn the basic concepts of causal inference and the state-of-the-art and techniques in uplift modeling. Next, we're going to look at the advantage and limitation of this approach and what is the unique setup that we have in many industry settings in constrained uplift modeling. And at the end, we are going to showcase some real-life applications and challenge implement these models in industry and also in academia that are also similar. As any tutorial here or any presentation also doesn't start without an agenda, right? So first part of this tutorial is going to cover the introduction to causal inference. About 40 minutes, and following that, we're going to dive deep in the uplift modeling, the specific part in Metalearners. And next, Hugo is going to take my place, and he's going to talk about tailored methods for uplift modeling, evaluating uplift models, and as well the cost optimization in uplift modeling. And finally, at the second part of this presentation, Anastasia is going to talk about applications and implementation challenge of both uplift models, but also other personalization methods we have. Before I start this part introduction to causal inference, I want to say, if you have any questions, please ask them along the presentation. Don't leave them at the end. We are more than happy to answer your questions here. I'm going to do my best to answer them. If I don't have an answer, please contact me during the break after the presentation. We can also have a talk, and I can also try to find an answer for you later on after this presentation. I want to start the causal inference part talking about causal questions that we have in everyday life, right? We are in UK, and a typical question we have, causal questions in prediction, right? How likely is it raining tomorrow? All right, so this is a prediction question, and this is very important maybe for British people and also for Dutch. And in an inference question, causal question, we have what makes it raining tomorrow. And there's these two different things about prediction and inference. And in prediction, we use all kinds of signals associated with the outcomes. So we are looking to the association of these outcomes. And in inference, we are looking to this causal relationship that happens between events. More clearly, in prediction, we look to the associated outcomes, and then we act based on it. And in causal inference, we actually look into these relationships, and you want to do something to make a change. And when you look to prediction, you're more like looking at how you enable personalized experience, and that's the part of this tutorial that you're going to see is based on the personalized experience part. And in causal inference, you use these causal relationships that make a change to facilitate the business and the product to make a decision. Back to our example about the rain, right? We have one factor that influences the rain, which is clouds. So if you see a cloud in the sky, do you expect to see a rain? So we are looking to the relationship of clouds and the rain, but also the direction. Seeing more clouds in the sky, does it has more rain or less rain, right? We all know the answers, but this is a causal question. And you also want to know the quantity, how much this actually is going to increase. Well, besides this, the cloud, this one variable that we have is there are more other variables, right? So the temperature, thunder, wind, all those might also cause rain. We are tired to know that also we have what we call it association is not causation. So many of the things might cause the rain, but they don't. They are only associated with them. So we might find that there is association between seeing more ants moving and rain, but they are higher correlated, but they actually they are not a cause of rain. So those things that in red they might be associated with rain, but they are not the cause of it. So in causal inference, we look at one aspect that we want to focus on. We want to control here the clouds, and we also look to all the other clouds and want to know if the clouds is actually going to produce the rain. And then we can determine if you can control for clouds in the sky, which we actually can't. Are we going to observe increase to the amount of rain we have? So back to the question is how to answer those causal questions. So that's it's a bit of an introduction to causality, and these are what I want to bring to you in this first part of the tutorial. One way to answer this causal question is towards the randomized control trials. And in Booking, we do it a lot, and many industry settings, and we have it, right? It's also called A/B testing, I mentioned. And we look to the population, and we have two versions of a role that we were interested to see, right? There is a causal effect. There is a difference between these two different settings. There are many things that influence for me that I can want to get this population, right? So the population size, how many people should I have? The power that I'm interested to do this A/B testing, and the minimal detectable effect. I'm not going to go over these three things in this presentation, but there are many resources online, great resources that you can find to learn more about them. So in the randomized control trial, well, as we do randomization. We randomize, we split this group, most of the times 50-50, or sometimes 10-90%. And we look to what we call the A, the base, and the control. This presentation, I'm going to talk a lot about the control, only the control term. So that's what I'm meaning by it. And you have the B, or variant, in the treatment side. We have a metric. We were interested to see the effect. And here we are looking at the review submission rate as a metric. And we want to compute what we observe as a submission rate in the control group and in the treatment group. If we run a t-testing after this experiment, we can conclude that maybe this experiment was conclusive, and the variant of the treatment is positive and is a better version of these two settings, because the difference we're going to see that the difference is actually significant. Sometimes this actually is equal, and we cannot actually tell that this A/B test is conclusive. We tell that it's inconclusive. And when we see an A/B test that is inconclusive, we have the two main hypotheses. Or the users, they don't care about those two versions that I showed to you, or some users love it and some hate it. So let's see a few examples. So an example users don't care is where we show these blue and white versions, and in the first part we have two groups of people, and they both dislike and dislike the same amount, right? So for the first group, they like everything that you show to them, and the second group, they dislike everything. So for them, doesn't matter the version of the website that you're showing, the version whatever of the settings that you're showing. But the other side is that some users might love it and some hate it. All right. But once you look at the difference between the two groups is zero. So this is what we see in experimentation, and this can happen. I use this example to introduce to you this what we call the individual treatment effect. On the first column here is what we say, what is a potential outcome that I can have from experimentation if I treat that user. And it's the second column, the next column here, is what is the potential outcome if I don't treat it. If I'm able to, for the same user, to see the outcomes if I don't treat and not treat, then I can compute this individual treatment effect between that specific individual user. All right. In the case of the first user, if I give the first version of a website to them, I'm going to observe some conversion or some response to that user. And if I don't treat it, I'm also going to observe it. All right. So imagine that you live in a parallel role where I can know that if I give you an example is if I give you a drug, you're going to react this form at the same time, at the same day, at the same time. And I go back to the past, and if I don't give you the drug, and I can see as well what is your what would be your outcome of how you react. This is an example in that we have. So what we see that after this individual treatment effect, if you average out the most right column, we can get the average treatment effect. So we compute what is the average, and here, for example, is at the end, the average that we observe is zero because we sum up, right? So everything is zero. This effects. This also goes another definition I want to bring to you is the condition average treatment effect. Let's say that I want specific in some users. I want a specific set. Okay, I have a we call a pre-exposure or covariate or a feature of this specific user, and I want to condition my effect on this type of users. So if I get x equals 1, I would only get the rows, the values on the first row in the fourth row. So that I would just take the average treatment effect for the two users where x is equals to 1. This is what we call the condition average treatment effect. Any questions so far? All right. Reality, we observe only one of these outcomes. So this is what we call the fundamental problem of causal inference. For one user, I can only observe, if I treat them, I can only observe this one of the outcomes, which we see these missing values in the here. And the fundamental problem of the causal inference is how can we compute this treatment effect if I cannot see what happens in different worlds, and what conditions can I have to apply that I have to assume that I can actually compute these average treatment effects. So if I had these two versions, I could determine what would be the treatment effect. As mentioned, the one user might only receive one type of treatment, and that's the received treatment. and that we have, and we can only observe one of the outcomes, right? So as we see, for y, for the last column, the outcome that we observe is exactly the numbers that we have here. The question, can we estimate these causal effects, is still from data. I still have this data and I still want to estimate this causal effect. If I get what is the effect of these users, the first group, the first two users, right? And the question, if I can get the average of the two for the treated people that I have treated and the people that I haven't treated, and this is if this is equally to what actually I want to measure, which is the treatment effect. What I have talked to you about is what we call going from the causal estimate to our statistical estimate. And this is where in causal inference, we call identification. We have a causal estimate that we want to estimate, and we have to provide an identification where we can estimate this statistically. We can say that statistically, I can estimate this value that is a causal estimate. And for doing this identification, to be able to say that these two things are equals, I have to provide some conditions. We have 4 conditions we have to follow. I'm going to go over 4 of them with a few examples when you have a violation in those conditions. First one we call exchangeability. If you see 2 versions of this, the blue and the white, if I swap these 2 groups, I should not expect a different value. So let's say I'm gonna randomize an experiment here, and for some of you, for this room, we're gonna give some treatment, and for the next room, for the other tutorial, we're gonna give another treatment. If I decide to give a treatment to this group or the other group, the results should still be the same. What this means is that if I decide to, for one group, for here what I call condition it as in t equals 1, if I observe the outcomes, if I had treated you, and for the other groups that I decide to not treat, but if I had treated them, these outcomes should be the same. This effect should be the same. Yeah.
Which is like, how do you verify or prove exchangeability? Is that just by saying that when you have the population you're sampling from, if you do that sampling well, and your sample is random and diverse enough, then we just carry on and say this condition is satisfied, or is there something formal?
Yeah, so this condition is mostly satisfied when you have randomized experiments, right? If you have an A/B test or randomized control trial, this condition holds for it. All right, so this something. If in the case that you don't have randomization control trial, you need to provide some techniques we have in causal inference to make this actionability hold. There are more information on it when you have we call observational data, and then you need to apply some of these techniques we call vector adjustment or front door adjustments to guarantee this. At the end of these slides, I'm going to provide more resources where you can find about it. But if you have a randomized control trial, this condition already holds on. Yeah, so as it was mentioned, and in the second equation also means that if you, for the group that is not treated, and you see this, you do the swap as well for the two groups, and what we want to observe the non-treated outcome, you're gonna end up having only the observation of the non-treated. These are equations they might be a little confusing, but what this also means, and the final what I want to mention here is that this means that the potential of the outcomes that we're going to observe are independent of the treatment that you're going to give. So if I swap these two groups, they're going to be the same. This is what happens in A/B testing. The next condition is we call positivity. We say that all the subgroups that we have in the experiment, they have a probability of receiving this value which is bound by 0 and 1. A violation example is if you have users from Germany that always receive the treatment, we cannot estimate what would be the counterfactual if they haven't received the treatment, right? This is one example. Another example is doing COVID, where if you want to estimate the beginning of the effect of the vaccine, but we are giving the vaccine, most of the vaccines were given to elderly people, and we cannot estimate what would be if these elderly people not have received the vaccine, what would have happened to them, all right? So this is a real example, real-world example. And the third condition is, we call it the consistency, where in the treatment, it doesn't have variation between them. So there is no degrees of the treatment. An example is, let's say I want to test the color blue, but each of you has a different browser, right? In the past, I don't know nowadays, but you could actually render those things differently in the browser. And you might end up having different versions of the treatment that you want, right? Even though everything is blue, but you might have rendered that button differently. And this is where you have different degrees of your treatment. Any questions? And then if by seeing different variants of this treatment, you're gonna observe a different outcome. And the last one is the interference, and this is a nice one. Is that a user that outcome is not affected by others else treatment. When this violates, an example in booking, let's say you're booking in a hotel, and the first user books one of these hotels, and after this hotel, a second person wants to book it, and the hotel is not available anymore. All the rooms are sold out. All right, there's no more availability. So the effects of the second user has changed because of the first user. Now, an example is in social networks. You decide to randomize something where is in a social network like Instagram or WhatsApp, and these users are connected, and we might tell that they are in one treatment or the other, and they actually don't see it. An example, when you release a new feature where it is specific to certain users, and these users share the same network, and some users see this feature and some users don't see that feature, right? And they might share something or users that have the two accounts or something like this. There are many resources available that tackles this interference problem, but you will need to guarantee that in an experiment, people don't interfere with each other. If we have all these 4 conditions, what we see in causal inference is that we can estimate those average treatment effects. There, as I mentioned, there are other resources when you have observational data, and you can find all of these 4 resources. There are many other resources online that you can follow about this. That you can, and one of these conditions that change when we have observational data is unconfoundedness, which I'm not going to go over in this presentation. Once you have all these conditions applied, you can get your data, right? And you can estimate. And now you can go and actually use your data and do the average, going from estimation to average. Let's walk through an example. Let's say now we have these 2 versions again, the white and blue. And what you can do, you can just use simple average to get what would be the outcome that you want to observe. Well, let's say submission rate, right? So if I see a blue color, I'm more likely to submit the review, and if I see a white color, how likely I'm to submit a review to the website. Now, back to the definition of Kate, and Kate is again that is the condition when you condition this expectation, and here we condition the expectation on users from Germany, right? We want to know what are the effects, specific effects on these users. We can go a little bit more on this condition. We can say we want to measure the effect on leisure travelers from Germany, and we can decrease from them. But if you go too deep on the condition, if you select leisures from Germany doing a last-minute reservations on their mobile, then we cannot use our simple average anymore. Your group becomes so small, and you cannot reliably measure that case. And this is where uplift modeling comes, and I'm gonna start this the part of uplift modeling. Any questions about the brief causal inference that I gave? It was very brief, but I hope it's enough for you to understand what I want to get to uplift modeling.
Sorry, I'm especially curious about the no interference problem. I was wondering like how Booking.com deals with the problem in practice, because for example, if you give a discount to some users and they post on social media,
yes,
I think that can cause.
Yes, so that's where as a scientist, you need to make assumptions, right? That if you have an experiment and you need to say that experience hasn't interfered, right? So then you need to guarantee that, of course, you have you don't have no interference. That's the assumptions that you provide. Most of the times you really care about the randomization unit that you're randomizing your experiment, right? If you're trying to estimate an experiment on users that they interfere with each other, you need to find a way that you have users that don't interfere with each other. An example of this is if you have geo-experimentation, where instead of randomizing all the users on your website, you go for geolocations, where you actually are able to separate, so like, okay, I want to London and Birmingham to be different cohorts, and then you decreasing your likelihood of people becoming the same network. All right, that's thanks for the question.
Thank you.
Any?
Why we cannot use simple averages?
Here, as I mentioned, as you have less group specific here, you don't have a lot of people to measure this. You might not have enough samples in your data to do this only simple average, and you might want to go from, as I mentioned in the beginning of the presentation, from the inference, because so far what I have told you about is the inference part, where you just use the data and you estimate this, and you go to prediction. And this is the next slide. Yes?
In the condition where the simple average is not realized anymore, so if such conditions do not hold, does that mean using simple averages is enough, or is it where does using simple average stand in terms of evidence?
Well, most of the times when you go for a simple average, we are looking to our sample size, right? And when you look to our p-test and we're getting the effect of this, we go for the sample size and you determine, like, is the sample size enough, right? And this what goes with more like on the power, how powerful we want this estimated effect to be, right? And also like other the effect, how much you want. But as if you have less data, if it's not enough, your estimation has a high variance to it.
So if sample size is high enough, then using simple average good enough?
That would be good enough. Question? All right. Well, as I mentioned, the uplift modeling comes where we want to estimate the state using machine learning. We go from modeling now, and we model this change in the outcome to the treatment effect. Now that's the model that it's going to learn about it. There are many methods in uplift modeling. Most of them, they are classified in Metalearners and Taylor methods. The resource of these methods are here. I put them on these slides, but they're also in the tutorial proposal. In this presentation, we're gonna go over a few of them. That is a basic methods. And Hugo is gonna tell us more about the constrained uplift modeling, which are additional methods to this uplift modeling techniques. I'm going to start with what we call the T-learner, which comes from the two-model method. The T-learner, what it does, you have this data coming from your treatments, so the left, and the data comes from your control. And you want to run two models where you're going to learn what is the outcome of your experiment, of your outcome of a specific user. All right. So you're going to fit one model, machine learning model, and you're learning this outcome. These models we call the base learners. That's where the meta-learner word comes from. The base learners can be any regression model or classification model if you're dealing with binary outcomes. And they can be logistic regression, bundle forest, networks, or any tree-based model. In practice, tree-based model works really well in this setting. That's what we see most of the papers that I mentioned, they go for. And after so as I mentioned, you predict this Y, right, from this X that you're trying to estimate. What is the Y for the non-treated? Well, what is the submission rates that you're expecting from this treatment, and from the non-treated? After having this model that I have learned, I can go to a specific individual here and be able to compute the individual treatment effect of this user. All right, so I just call that the first model once with the same features, and I call the second model the same features, and I just take the difference between them. And this is the treatment effect. Questions? Well, what are the drawbacks of this T-learning? The models are trained independently, which means that they might predict some spurious effects. An example is here, where you have data from your T equals 0 means the control, and the T equals 1 means the treated, and you don't have enough data for the treated, right? And your model doesn't learn this complexity that you should observe. You learn for the control, but you don't learn in the treatment. So the T-learner doesn't work that well if you have less data in one model than the other model. One model is, let's say, put it like this: one model learns better than the other. All right, you have no guarantees. One way to overcome this is what we call the single model, or the S-learner. In Uplift modeling, we have many of them. We have S-learner, T-learner, X-learner, and many others, Y-learner. One of them here is the S-learner. And what it does is we're not gonna do two models. We're gonna just do one model. And instead of now we are gonna add the treatment as a feature to my model. And I can just then call this model twice. And for once I just set the treatment equals 1, and the second call I said that the treatment equals 0, and I take the difference between them, and I say that this is my treatment effect. So, of course, this model has also drawbacks, right? What if the model learns to ignore the T? This can happen, and so this might happen to your model, right? The model just ignores the T. And an example where this happens, if you have any model that try to do some regression, and you also have a high regularization in your model might decide to drop that feature, right? So if you have a L1 normalization, and the model just gonna drop that feature. And
Yeah, when you say these regression models, what are the typical features that you use for these things?
Depends on your problem, right? So the features you're talking here is in anything related to the user. So it can be like where he's located and so on. So anything characteristics that you want to take and want to personalize for that user. right? It can be historical behavior or anything on the past before the experiment. And these features themselves, they need to be features that happened before, of course, nothing because you don't want to have an interference. Yeah.
Are there any guarantees on, how good or the treatment that the testing this approach? Because I can imagine that if the model, you can imagine that it's just random, it will give you a random number, right?
Mm-hmm.
In this case, you wouldn't probably trust the estimate.
Yeah. What would happen is if the data is basically like random, or if the effect is super small for this model, the model will not capture, right? It's so small that you're not going to learn what would be the effect of that treatment feature, and that's the biggest drawback of the S-learn. Yeah. Any questions here? No? Yeah. Yep. Yeah. Good question. As I mentioned, the two had drawbacks, right? One is if the S-learner is good, if your treatment has an effect that is not to be detectable, all right, and you don't have a lot of your data is imbalanced. Let's say you have 90% of your data is from one treatment and 10% from another one, but the treatment that you're gonna give is very effective that you're gonna find this effect from in the model, right? Whether in the T-learner, that you don't have to care about. The T-learner, if you have balanced data between them, if both models are able to learn their complexities, the effect is going to be detected by the T-learner, right? So I think then it becomes a use case, right? I have a model or something I want to personalize on my website there. I think my effect is very small, but my data, I'm willing to have 50-50 split on my data, right? So I'm gonna control 50% of my website and 50% of the other users. Then you would go for a T-learner would be able to guarantee that you can detect this effect. Whether if you have the S-learner, if you say that your effect is too small, then you shouldn't go for an S-learner. In theory, right? In practice, you have to go and test it. In many scenarios, the S-learner works really well, right? So this is something we have observed in practice as learner goes and does learn well.
Treatments are coordinated with S-learner. I mean, they have some common
Yeah, so the S-learner is going to be able to, let's say, learn this common thing, right? While the T-learner is not, the two models are gonna learn separately the effect, and let's say they're gonna learn twice those things, and where the S-learner, you're gonna share them together. All right. The last model for my part, I want to share with you. We call it the X-learner, and it's a bit more complex. And I'm gonna spend some time here before she will take my place. And recall that the T-learner I mentioned to you, it learns these two models, right? And the X-learner is what we call the stage one of the X-learner. And the trick part is so far we have trained in these two models, but we haven't used it yet, right? And what the X-learner does is actually using, again, these models. Why? Remember the potential outcomes that we talked, what would be the potential outcome? If you have a data from the treatment, here a condition on treatment 0, the Y I can observe from this, right? Because I have observed what is the outcome if I don't treat these users, right? So that's what we call, so just the control. What I can then do, I have learned a model that learns for me the outcomes if I have treated them. can I just plug them here, right? And do the same for the treated variables. And I would have this counterfactual, this fake data, right? Put it like this, where simulation is a better word, where you think you can just take this difference, and then this is my counterfactual estimation. So it's an estimation of an estimation. We're going to put this in of these variables, and which is the output of one model, and we're going to learn another two models. It's where the X comes from, and we're going to learn from this data that I mentioned that we created syntactically, right? And this X learner is going to learn this from this counterfactual outcome, and then what we have to do is to combine these two models. The combination of these two models is a bit tricky, because we introduce another variable to combine it, to introduce another model. And this we call the propensity score model, where is the likelihood of this variable being from the treatment. Now, bear with me. I want to resume what we have done so far from the X learner. So we first start with two models, right? We get the output of these two models and we cross them. So here's the X comes from. We fit another two models, all right? And now we need to combine them. And we learn a new model, a fifth model, where it's the likelihood of this variable that this user has been coming from the treatment. We combine them, and it's going to be our at least final treatment effect. Now, let's walk a little bit about this combination and try to reason about it. So the first part, I'm weighting some X based on this model, tau 0. And so if you look at this tau 0, why I'm waiting for this is that this probability that this EX is a probability is coming from the treatment. And the reason from the authors of this method is that, all right, so the probability, the treatment variable coming, the treatment unit coming, comes from higher from a model, which is T0, and the T0 that uses actually the U1. And U1 here is the model that learns the treatment. So I should weight more this model that comes from the treatment, because the assumption here is that the model has a higher quality. So that's how they come with this weighting mechanism. And the same from here, right? So you tau 1, you learn a model. So 1 minus this propensity means what is the likelihood of this user has come from my control. And this tau 1 actually what it has is the model that learns to the control before. So this is the reasoning on the X learner, and just point out there are other variations of this combination. The authors as well mentioned that there are other ones, and you sometimes you actually don't need this combination. You can also use the output of the two models, but something that you also need and go and try. That's not the single variation. Back to that image that I talked about, the T-learner, that the drawback to the T-learner was to be able to learn this nonlinearity that we have in the treatment, in the blue dots, that we don't learn once we have fewer data. And the X learner, what it tries to do is to create these counterfactual outcomes and give enough data, creating this counterfactual data that you can learn this nonlinearity. What this means in conclusion that you can take from the X learner is that the X learner can use the information now from the control group and derive better estimations for the treatment group and vice versa. all right? Compared to the T-learner, the X-learner does, if you see in the paper and the results, that does a better job in correcting this wrong estimation that has nonlinearity. And in general, X-learner performs better, as I mentioned here, than when the treatment is much larger than the other. It's not the final solution for not using S-learner or T-learner that X-learner is the combination of both. That's not what it means here, is that the X-learner actually covers a bit of the drawbacks of the T-learner, right? I think I finished my part a bit earlier, but if you have any questions about X-learner before Hugo take my place. I know the X does a very complex things, and I recommend if you're interested in the X-learner to go in the paper as well. It's well explained. But if you want to try some of these methods as Metalearners in the beginning, you should go for the S-learner and the T-learner first before actually going for this very 25 models instead of just 1 or 2.
Yeah. You said it just performs better than the B.
Yeah.
How do you compare it with X? Because one thing I see is X has too many estimations that might contribute to a bad performance.
Yeah. So that's the thing. The trick of the X-learner is that there is no the guarantee here, right? So it's hard to find in reason about it. And I must be honest with you. The X-learner is very hard to actually work in practice. Let's say if you want to deploy like a model in production or you want to work with it, having to maintain 5 models at the same time is really hard. In most cases, people prefer to go for a simpler version, the S-learner and the T-learner. That you have to look at your scenario, right? Now, how you test and see, you really have to do the experimentation and to find out, in your case, in your data, what works best.
I think I have anything. So in X-learner, you have class the model and so does that imply that X-learner assumes there is some kind of relationship between sort of data or there's not the
Yeah, it does assume, right, that you can, of course, as a T-learner also assume that you can take this effect out, but the idea of the X-learner of crossing is to find this counterfactual data that you don't have in real life. So the idea that you need to use one model's prediction to actually find what would be the prediction if I had treated or not treated that user, then that's how you create this counterfactual data to train more, to have more data to train your models. That's the main like intuition of the X-learner. Yeah, so I'm gonna hand over to Hugo. He's gonna spend some time here until we go for the break. And yes, thank you. And Hugo.
Thank you, Felipe. So I'm Hugo. I've been almost 2 years at Booking. Before that, I did a PhD in machine learning, where I created new algorithms for interpretable machine learning and other areas with statistical guarantees, and also worked at Huawei for a while. Yeah, now I'm at Booking. So I just wanted to say, because of some of the questions that came before, you were asking about guarantees. And I have to say that the literature in causal inference sometimes is slightly of a mess, because you have people doing research from computer science, have people doing research from marketing, and you have people doing research from economics and mathematics. So if the methods usually come from mathematics or economics, they come with a lot of proofs and guarantees. So not the X-learner, but the R-learner, so another one, was done by Steven Wacher. And you have all the guarantees that you can check, because he proved that it's asymptotically converges to what it should. The only thing is that the S-learner, for example, works in this scenario because we have randomized data. And so we assume that we have this balance between both sides. The problem of the regularization is that it can create a bias. So your estimations are not guaranteed to be correct, but the strength of the effect can still be correct if the bias is constant for all the instances you are training on. And also the X-learner was developed for observational data. It can also work on randomized data because by default, if it works on observational data, it also works on randomized data. So it also has some other techniques inside to work well under observational data. That's some of the things that I just wanted to say before starting. For tailored methods, I just want to cover a little bit of uplift trees and to give you an intuition why people created. So these are the most tailored in a sense because they only work with randomized data for, either conversion or regression if people created them for that purpose. So usually the main idea behind trees in general is that you have a data set. In this case, I'm just focusing on a binary outcome, so converted or non-converted. And people want to split this data in the best way possible that you have converted on one side and non-converted on the other side. But in the case of uplift modeling, you have a treatment group and a control group, right? So the data is divided between these two groups. And the main idea is that you want to have the biggest treatment effect in the splits you make. So ideally, we would like to find this amazing feature that would split with 100% uplift to one side, with feature equals to 1, and it would have a perfect downlift, so negative conditional average treatment effect. So positive on one side and negative on the other. But reality is a little bit more messy. So you don't really have perfect splits. You have something in between. You have some noisy estimates that the features, this is the best split that you can actually do with the data and the features you have. And so the usual way of growing trees, like in classification and regression trees cards, is that you greedily make splits. You find the feature that best splits the data at each point. And in this case, is more or less the same. But so how do you measure the quality of these splits? Use divergences. And I mean, here we just call them divergences because they don't have the properties of what the metric is, but some of them are metrics, like the first one I'm going to mention. And you just measure what's the gain I get from splitting the data, right? So I have this quality before, and I will show you one example of a quality you can measure for these splits. And you calculate the quality after you split the data into two parts. And so the simplest one that was proposed, I mean, it's also proposed before in normal trees, is just the Euclidean distance. So you calculate the probability on the treatment. So in this case, we have 4 by 6, and you compare that probability with the one in the control, which is 2 by 6, and you want to maximize that in the split. So the biggest the gain you have, the more you will get. So you choose the split that maximizes this. You actually have a lot of divergences. These were the 3 first that were proposed. I mean, we kind of know what they are. Euclidean, Kullback-Leibler measures the difference between probabilities, and chi-squared is the idea behind the test. But I mean, at this point, people have invented, I don't know, a lot of them, of these splits. In the Causal ML package online, you can just check. There's a lot of them, and they all promise that they have improvements over the other ones. So yeah, it's again, you test the one that works for you, and one of them should. Do you have any questions here? Feel free to ask. Yeah, so the main idea of how the trees pass to forests is exactly the same as random forests. You generate samples, you learn a tree there, you can do random splitting, you can do all the things that you do with random forests. You learn a tree, then you learn another tree, and then you average out all the predictions. So there's more tailored methods that we're not covering here. People are constantly inventing new methods, but these are some of the ones that are more established, that have been here for longer, since the 2000s, 2010. So these methods exist already for quite some time. Do you have any questions here before I pass to another part? Yeah.
Just to review is the end goal of the tree is to have child nodes that will split the data very evenly between what we know, in this case, we the converted and non-converted.
Yeah.
We know that at the beginning, the root node, who's converted and who's not.
Yeah.
Okay.
So you know who is converted and not converted, but you don't know how each feature separates that, right? So if you have a binary feature, is like, let's say if someone plays football or not, I don't know, just thinking of something. It's a binary feature, and then based on that, you wouldn't get these perfect splits. Most of the times you get something noisy like this. And then what you do is that your algorithm goes, in the perfect scenario, you'd go over all the possible splits and would say, oh, this is the best split. This feature with this split is the best one to separate at this point. And then after that, you do it again and you learn more, and the tree continues growing.
So the end goal of building up really understand the effect of the features.
Yeah, is to find what are the subgroups in the data that have the biggest causal effects, right? And so you are interested both in positive one and in negative one. So you want to find the ones that separate better and have like a purer effect. Yeah. So how do we evaluate uplift models? That's a very important question. And a lot of times when you have supervised scenarios, so when you know the truth about what you are doing, so in classification, in regression, you can just compute mean squared error or your favorite metric, because you compare your results in the test sets and you compare it against what you predicted. And you see if it's correct or not. And you can calculate this metric. But as again, we don't really have a ground truth here. So we cannot calculate these metrics as mean squared error directly. But we can do it on an average scenario. So what you end up doing is you train your uplift model, and then for your test data, or validation or training or whatever you want to, where you want to measure, but let's say the test set, you sort the instances by their effect. So the one that has the highest prediction, so one promises to have 100% uplift or conditional average treatment effect or effect, you put them to one side, and the ones that have the lowest, you put to the other side. You sort them in this way. And then for each group, I mean, you just do samples. A lot of times people do deciles, so divide this in 10 parts, and you can just calculate the average, because in this case, you are going to have units or people in this case that are in the treatment and are in the control. And then you can calculate this average, because then it's going to be, again, under the assumptions that Felipe told us, you can get an average treatment effect for this group. After you calculate this average, you just calculate for all the groups sorted in this way. And you can get these bins, which are called lift gains plots. And these plots, you just show that for each bucket, imagine if I would have divided it in 10 parts, you would have had for each one, how much uplift or how much increase in conversion, if we're talking about it, would you get by doing these treatments in that bucket? And supposedly it should go down, but as our predictions are not perfect, also the buckets sometimes don't completely match. And then what people do a lot of times is that they create a cumulative curve. So they want to see if the sorting of instances or users or units is correct. So if the sorting is correct, you should start by having more uplift or more effect in the beginning, and then you end up having less effect in the end. Any questions here? I'll go further into this, but if you have any pressing questions. So what people do a lot of times is an uplift curve. So let's go over an example. So remember those submissions. Imagine if we asked people to submit, and under one scenario, we got 1,000. So if we didn't change anything in the user interface, get 1,000 people that submitted review forms about their stay. And if you change the user interface, you'd receive 1,500. So in total, you get more, right? You get a little bit more of the users that actually submitted by doing this. So the first 2 points you can establish in this curve, in this uplift curve, is the 0, right? So if you don't show this treatment to anyone, you get 0, right? So you get exactly the same thing. Control, there's no effect. And if you give it to 100% of the people, it's just you give treatment 1, you get this 500. I just have to say here a caveat. There's a lot of ways to calculate these uplift curves. I'll go a little bit in the end of the subtle differences between them. But, you know, some people would scale it up, and instead of 500, they would say, because the control is 0 and 1, then it's 50-50. So what I want to know is how it would be in 100%. So then it would be 500, it would be 1,000. But there's different ways of calculating it. This one is the easiest one to present, so I'll go over this. So we have the 500, which is the end, which is treating everyone. And then we know the random curve. The random curve just tells us that if I would just treat 50% of the people with the treatment 1, it means I would get half of that. So I would get 250. So those are the first 2 things we know. And then if we make an uplift curve, we hope it's above the random line, right? Like as an area under the rock curve, we prefer that it's better than random. And the intuition here is that in the beginning, you have more, you sorted the instances or the people here in this case by how much effect they have. So in the beginning, you hope to have a bigger increase, and then it kind of plateaus. And what is interesting is that in certain kinds of, especially marketing campaigns, there's also a negative effect. So there's people that really hate their emails or some sort of message, and they hate it so much that they actually react worse to it. So sometimes if you don't give the treatment to everyone, actually you are better off than giving it to everyone. But this honestly just happens for certain types of campaigns. So what I want to say here is that can be a negative effect. So you can even go above the endpoint here. And how people usually measure, oh, sorry. Yeah.
Check that your framework works. What would this look like?
So if you run an AA test to see if this, what would work, sorry?
If you have a testing framework, sometimes you want to make sure.
Oh, yeah.
Nothing wrong, so you have an AA test. What would happen in this scenario when you're doing the skate method?
Skate method. I mean, in the end, you hope that you achieve a similar amount. So let's say actually, just giving the treatment, not uplift or.
So you have two control groups, so I imagine that the right dot's going to be at 0 as well. But I'm wondering if you're going to have some kind of overfitting where you will find random uplift in some group. So you would still see a little curve, even though there's no real effect.
Okay, yeah, now I'm understanding what you're saying. Yeah, so you hope to have 0 effects, in the end, but you can always have noise. So probably if you'd make buckets or something like that, you could have some fluctuations, but hopefully if you have made a good enough sample, by the end you'd go to 0. There's actually didn't think too much about it. So I was thinking that you were asking actually in practice how it happens is that if you'd have a model that works at this working point of 70%, then you would compare this model working at 70% with a control of running with nothing, right? So that you could measure this difference. Usually it's also interested to run it against the same baseline where it was created by giving it to everyone. So you have both a control group, a baseline that it's the performance of giving the treatment to everyone, and the model. But depending of what you are doing, it can be costly. So it really depends of the experiment that someone is running. So to measure the quality, people came up with exactly the same thing as in machine learning. So the area under the uplift curve. But here to normalize it in an order that it's between 0 and 1, you calculate it just until the random curve, and you calculate it and you normalize it between the random curve and the perfect curve that you would get with the points, even if it would be completely infeasible because you don't have those features. You just want to have a value between 0 and 1, where 0 is random and 1 is perfect. So the caveat here is that if you, for example, don't give just one treatment, imagine we don't have just one of these user interfaces. So if you have multiple user interfaces that you are testing at the same time, and you are trying to check which one is the best, the main idea is that you can only give one treatment per person, right? Even maybe it's not giving what already existed, so the 0, or any of the new pages that you were thinking of doing. So in this case, you select the best treatment effect of all the treatments. You sort based on this treatment effect of the best one. And again, you just calculate the average against 0, against the control group of doing this treatment effect of the best case. And you can do the same curves and the same things. But again, as we are entering a scenario that there's multiple treatments, there's more problems that arise here. So maybe you predict something and you assume that you're going to get treatment 2, and then there doesn't exist treatment 2 for that person. So a lot of times you lose some data and you have to make some choices that are more complicated under these multiple treatments. And just the last thing I wanted to say is that there's different ways of computing uplift curves, and a way of separating them is between ranking and counting. So what I mean by ranking is you can put treatment and control samples all in the same kind of analysis. You just say the ones that have the biggest effect, you put them in one line and you calculate these averages here. Or you can separate. So you have a line for treatment and you have a line for control. And then you compare, oh, how did it go on 10% of treatment and 10% of control? And the same can do for the counting. You can count it on an absolute term. So in absolute terms, in the end, like what I did here is that you end up at 500, so the maximum possible. Or you can do it relative, which is you would normalize by each instance. So you would get, in the end, divided by the total. So it would be a mean effect over everyone. And there's a last little point. There's something else that's called Kinney curves. I don't want to confuse you more. And they are slightly different in their definitions. They almost give the same, but it's just the way you make the sorting. So if I could give you like a rule of thumb, to go home to evaluate this, usually it's better to sort them all together. Yeah.
I'm just wondering, when you just average people that you're looking for statistical significance, and when you're giving that curve, is there some kind of uncertainty about?
Yeah, you can create an uncertainty over the curve. I mean, a lot of times when people present it in papers, they make a nice curve, but you can also make it like with the uncertainty by doing bootstraps over those, because you are doing cumulatively. And then for each decile, let's say, you can just make a bootstrap and calculate how it would go. There's some work that people also found ways to calculate it with other tricks that are not bootstrap, but yeah, you can just calculate confidence intervals over it. So by the end, you should have a tighter confidence interval, and then the beginning is bigger because you have less samples. Yeah, so the last thing, just the rule of thumb is that you'd probably just do it together in one sorting, because when you separate it, there can be problems out of the fact that the top ones in the control maybe not the same the top ones in the treatment, while in the sorting you guarantee that they are sorting according to their characteristics that you use, the features you used. And the other thing is that, yeah, between absolute and relative, it really depends on what you want to see. In business terms, we usually want to see what we get in absolute terms, so that's usually what we go for. So that's the end of this part. If you have any questions, feel free to ask. Yeah.
Regarding separating and together, I want to ask, is there any way to choose, or it depends on, is it possible that will depend on the model or the well?
Oh.
Separate models, so
yeah. I think, I mean, this is mostly my opinion. I don't think it's really related. I mean, of course, the characteristics of the model will probably make it better for a certain kind of curve. And the sad thing is, depending how you make the curves, different models can come out better than others. So what really matters is that which way you choose to make the curves represents how you make your business decisions. So if your business decisions are based on kind of A/B tests, or how would this compare with a control group, you'd probably would like to look at them together, because that would mean 100% of the people, right? Although there are two different groups and you hope that they are homogeneous between them and you could exchange them, it's better sometimes to just, yeah, a certain grain of salt, just put them together and see.
So in which case, separate information? I think I.
Yeah. No,
yeah,
as the separate, actually, I don't know. But this paper that I set here, they go over all the possible combinations, and they just talk about their case, what it represents. But I've said that, yeah, I haven't seen like great definitions about this. Like the latest work that I saw that was quite cool is by Susan Atty and Stephen Wacher. So you already have like two big names in economics, and that they were talking about Gini curves, and they put everyone in the same curve. So I mean, if they do it, I say that it's a very big case for that curve. But yeah, I'm not sure when the separate curves make sense. Yeah. Yeah, the cool thing was that, I mean, everyone does it in different ways in their papers, and they, at one point, because they were doing learning to rank for Uplift modeling, they just checked all the papers and saw how people did, and they realized that they all do it in a different way. And yeah, I want to talk now about costs in Uplift modeling, because a lot of times when you do Uplift modeling in e-commerce, you not only want to maximize the treatment effect that you are gonna make of some metric of interest. It can be conversion, it can be revenue, it can be long-term value, anything you can think of. But there's always usually a cost to a lot of the problems that we're dealing here. So how do you take into account the cost too? And oops. what I want to say is that usually what you want to do in a campaign is that you are giving something. You make a change in the UI, you change the user experience, you make a promotion, and you hope to receive something in return. And this is what you want to measure. So the conversions, the loyalty, etc. To talk about costs, I would like to say something that usually doesn't appear too much in Uplift modeling, that there's always costs, right? And before someone does Uplift modeling, they should think about how much it's going to cost in terms of infrastructure, headcounts, and exploring the data, right? Because this is a cost that exists, and mostly this is a thing that is done by directors and product owners, but this should be thought. But a lot of times, Uplift modeling just ignores this part of the costs because you assume that if you do this well, you'll make money, and this cost is virtually zero, although it's usually quite big. You assume it's zero in the long term of what you are doing because you are going to continue doing this for a long time. So after this, I'll kind of refer this as non-existent, but I just want to make a little bit of a difference compared with most of the cases in Uplift modeling. So the first case I want to talk to is treatment personalization, right? Here actually there's no cost most of the times, except that operating cost, but there's no cost of making this change, or there's no virtual costs of making this change in the website. The website is already running. We're just saying, how was your stay? And we just want to estimate what's the submission forms. So if people in the control group have already seen the blue banner, the treatment is going to be see the white banner. And in this case, we just want to measure the Kate. And we want to maximize this expression. And what this means is just ZY is just 0 and 1. Will I give to this person this new treatment or not? And the Kate is just, will they submit more forms or not? Is there a higher chance of them submitting the forms or not? And we want to maximize this. And in the end, for the ones that they had the positive case, so that they get an effect out of showing the new banner, we want to show them to them. So how was your stay? In white, we want to give this to the ones that had a positive effect. The ones that have the negative effect stay with the old version of the website. In this way, you can personalize, but you can generalize this to many cases. But in general, you can assume that there's no cost in doing this kind of treatments because the cost you have are more from infrastructure, and you can assume that, you know, they will average out. That's mainly the idea, but someone has to do these calculations behind the scenes, right? To make sure that your project is going to make more money than it's going to cost in terms of people. The other case is that treatments can have a fixed cost. So imagine that we, instead of sending this email or asking people how was their stay, we'd send them a letter home. So these letters, maybe they don't cost much, but we're going to send them to everyone independently if they actually going to respond or not. So we're going to have this cost anyway, independently. So this is a case where the treatments are fixed. And if we make a matrix of, you know, the outcome of interest, here 0, 1, that people did something, they converted or they responded to it. So they submitted the form. And treatment 0 is the control, treatment 1 is we give them the letter. We have a cost independently of what they do. So we'll always have a cost. Then there's fixed triggered costs. So imagine we would be a big company that ships things to people's homes, which we're not, but imagine we are for 1 second. And in this case, imagine if the shipping is constant, you would have a constant price for shipping, right? So you'd have every time someone books something or someone would buy a product, you'd have this cost, but you only have this cost if they actually buy something. If it's 0, you actually have no cost. So this is an interesting scenario that happens a lot of times in e-commerce. And the other case is if you give a discount, for example, we can give a car discount of 15% and you can use it in any car. But in this case, the cost is not fixed, it's variable. So it only happens when people choose, but it can be whatever people choose. I mean, we don't even know what they're going to choose. So we just have these costs anyway, and it can be variable. So just to summarize, I just want to go a little bit over the types of costs that we talked about. Operating, you don't usually think into it when you are doing uplift modeling, but you should do it in the project planning part of it. Then there's treatment dependence, everyone gets it, and there's triggered costs. In e-commerce cases, most of the times we have triggered costs because out of giving coupons, out of giving promotions, out of giving special things, usually only if someone actually buys with that, we actually have a cost. Otherwise, there's nothing because no one bought, you don't get anything, but we also don't incur a cost. So I already showed personalization in a sense that didn't have a cost. Now I want to go to how you look to uplift in conversion and revenue. So imagine we have Bob and Amy, and they're two nice people. And they have been to our website and they had one conversion, one non-conversion, and there's some revenue. And when I'm talking here about revenue, I just want to say that it's net revenue, so already take into account minus the discount. So you can, if it's easier for you, you can think of it as profit, but you know, it really depends of how people talk about things. But in this case, net revenue already removes the discounts out of giving promotion. So again, as Felipe told us, we don't know their outcomes if they were only in the control group. We don't know how they would behave if we actually gave them a discount. So if we decide to give them a car discount of 15%, how would they behave in terms of converting and in terms of revenue? But imagining for a second that we have a perfect world, we can see their outcomes. And we can see that in the case of Bob, it actually was good, right? Because he was not going to book without a discount, and with the discount he booked. And the revenue was zero, and actually made the revenue because otherwise he wouldn't have booked. In the case of Amy, actually she just booked the same, right? And the revenue decreased because she decided to book another car, and with a discount, and the price was even lower. So in the sense, we lost some money out of doing this promotion. It doesn't have to be bad that Amy did this or good. There's not this thing. It's usually you have kind of a budget that you are optimizing for, and you don't mind offering this to your users. You just don't want to overspend the money you have to go overboard and spend too much money. So in practice, we can calculate it again. Oh, you can ask a question. Oh, I thought you. If you have questions, feel free to ask. So in practice, you can calculate the same thing. You can calculate the conditional average treatment effect, the uplift in conversions by just calculating this average. And if we are under a randomized trial, we can separate them. The same thing goes for uplift in revenue. You can just do the same thing. Instead of being a binary feature, it's a continuous feature. You just calculate this average and you just subtract them. So as I see it, and this is my opinion, so take it with a grain of salt, there's 3 different levels of doing uplift modeling. And I call them levels mostly because there's different levels of complexity into modeling this. I say that maximizing conversion is simpler, it's not much simpler than other cases, but most of the methods that were developed in the early years for uplift modeling focus on conversion. So in the 2000s, the first papers focused on conversion. And so this is a better studied problem that we have more literature, more tailored methods, more uplift trees, and things like that. And so in a sense, it's easier. So you just want to maximize for each instance or for each person, you want to maximize their conversion. You see, does it improve by doing this treatment or not? You can imagine the submissions. Did it improve? Yes, you do it, you make the change. If not, you don't make the change. And so in the sense, you just look at one individual person and you see for this person, did it help or not, after estimating over the whole data. Then you can do maximization of unit value. So you can find your utility function. It can be your long-term value, it can be your revenue, it can be another thing. It's a continuous metric. And in principle, it shouldn't be too much harder than conversion. But in practice, due to the real world cases that end up happening, and that revenue has a log normal distribution or an exponential distribution with a long tail, this ends up being a little bit trickier to model, and people don't discuss actually so much this in practice. Oh, go for it. Yeah.
How is maximizing the unit conversion different from just saying it in a maximized rate?
Oh, it's the same.
They're the same.
Yeah, theoretically, yeah.
Is there an instance where they aren't the same, for instance, like utility?
No, I mean, so utility is just to imagine that you find a metric that represents what you really want to give for the user, right? So you realize that what the user really wants is to be fulfilled in life, and you can measure this from 0 to 10. And if you can have this metric, you could maximize for it, right? A lot of times the companies have this idea of long-term value or lifetime value. So how was the value of a customer for the whole life? And then you can just maximize that. The last case is that you can maximize the total value. Either you do revenue, utility, or something else, and you can do subject to constraints, such as a budget or a return of investment. In this case, you don't look at one individual and decide, do I do it or not? Do I give this treatment or not? What you do is, based on all the individuals that I have seen, should I give to this one or not? Because you are taking into account the budget, and some ones can be more expensive than others, and you end up being in a scenario of constrained optimization. So, constrained uplift modeling. I'll start with one treatment, and then we progress from that. And so I'll just give two scenarios so you can decide to treat a user in order to maximize the treatment effect. It can be the booking rate, and you can decide to hurt some budget. I mean, your company says, you know, it's Black Friday, we want to make everyone happy, we want to make more people book, get these budgets. But you can have different things. So it depends on the priorities, can hurt some budgets. Or they can say, maximize, for example, conversions and don't hurt the budget. We can only make money out of this promotion, so we don't have money to spend. So just give to who would really change their decision by giving this. I will focus on using the maximization of conversion as an example and the budget as a constraint. But a lot of times you have return of investment constraints, and you can just imagine that if you say a return of investment of 1, so I make the same cost as of money I make, is actually equivalent to a budget of 0, right? Because if I make the same money as the one I spend, is the same as having 0 budget in the end. And this transformation can hold, and this, yeah, so they are quite similar in that sense. So from a mathematical perspective, or again in this scenario, so we want to decide for each user, do I 0 or 1, do I give it or not this promotion, this discount, this card discounts or not, to improve the conversion, and I subject it to a constraint. And here I'm saying minus revenue, because yeah, if it's positive, you are making money, so you're not hurting the budget. And if it's negative, it's when you actually, when the revenue is negative, is actually when you are hurting the budget. So you just want that the sum of the total loss you make, it's below that budget. So just go over this to not get people overwhelmed. It's just a normal formulation of constrained budget. You're maximizing something subject to a constraint, and we are just deciding how to assign it, 0 or 1. Do we give this card discount or don't we give this card discount? I'll now go over the classical way to optimize this, and this can be a little bit overwhelming for some, but I will then go over the intuition, and it will make it much easier. But I just want to say that if you just want to maximize a constrained optimization problem, the general way to do it is just using Lagrange multipliers. So you just bring them up and you solve this unconstrained problem. And then you can solve, so the previous problem is called the primal problem, and the second problem is the dual problem. And you can solve this dual problem, which doesn't guarantee that the best solution of the dual problem is the one of the primal, but under certain conditions, and actually almost always holds when you are talking about budgets in real cases, the solution of this dual problem, which is just you want to find the minimum lambda that maximizes this. And don't get, if some of you are confused, don't worry too much. I'll go over the intuition of all of these if you say. And what this basically means is that if you'd have this transformed way, the solution of this problem is just for whoever is above zero for the uplift in conversion minus this transformed revenue with the lambda. The lambda kind of creates a transformed outcome. You give it the discount, and otherwise you don't give it. And this problem actually in literature is usually known as the knapsack formulation. And the thing about the knapsack is that it's a backpack, and you're just carrying your backpack. This backpack has some weights, which is that it can handle a maximum of a B budget of weights. And you have some items that you want to add to your backpack. And you want to add them in a way that you maximize the value you can carry with you with the minimum weight possible, right? And this intuition for us is that the value we want to maximize is the kate of conversion. So we want to maximize conversion with the minimum cost possible. And the approximation solution to this is to just sort people by conversion divided by costs or by negative profits. And what this means is you want to add first, you want to sort people first that have more conversion by the minimum cost possible you have. This makes sense. And what this would mean is that in practice, imagine that in one side of this red line, you'd have 10 conversions that cost €1, that you'd spend €1. In the other side, you have 5 conversions per euro spent. And you can think of this like, okay, now I got 1 month of data, 2 months, whatever you have. And you say, oh, you want to target an amount of people that doesn't cost us more than €5 per conversion. So you stay above the red line, and you can use this as a solution. And this can also be seen in 2 dimensions. You can look at it in 2 dimensions, kind of a multi-objective problem, that one of the axes is your value, how much extra conversions you are bringing. So the kate of conversions, so extra conversions. And the other case is the kate of revenue, the negative revenue. So what this means is there's 4 axes, and they have very clear interpretations. In this left side axis, what you see is that you always have positive conversion, and you have always positive profits and revenue. And in that case, it makes never makes sense to not give this treatment, never give this discount, because you always make money and more conversions out of this if someone ends up in this area with the treatment. So it's positive conversion and positive revenue in this case. Oops. The other case that is very clear is that you have negative conversion and negative revenue. So it never makes sense to do this because you want to maximize your conversion, and you basically just hurt your revenue. So this is the no-go area. This is just a very weird area that just exists mathematically, honestly. I mean, you can always have points there because you're making estimates and this is noisy, but usually this doesn't really matter, which is just you have negative conversion, but you actually are making money. So I'm not sure you want that for your business, but in very specific scenarios, maybe you want, yeah, that's just it. And the last case is the area where decisions have to be made. So the other ones don't have any problem with decisions. This is the area where decisions have to be made. You make some conversion, but you also hurt some of your revenue. So the decision is, how much do I want to be in this area, right? If you have a negative budget, if you have a zero budget, you can be a little bit here on average. If you want to optimize your campaign on average, you can be here because you are making money from the green area and you are losing some money in the yellow area. But it really depends on how you go there. So this is just the intuition between sorting by value divided by weight. So uplift in conversion and uplift in revenue. How do you actually solve this? So this is the naive approach that just gets really noisy very quickly. It's that you have two stages and two models. So if Philippe already told you, an X learner has 4 or 5 models, and then you have 4 models for Y and 4 models for revenue, this can escalate quite badly, quite quickly. But this is the naive approach. So you have a model to compute the improvements in conversion, so how much more conversion you do and how much more revenue you do. So you have 2 models, you estimate this, and after that, you just make an optimization. You find your solver, you either do the Lagrange solver that I showed, or you just do the sorting by value and weight. And with this, you just can get your solution, but I'll have to say that in practice, the errors start propagating, and this can be complicated. For one treatment, it works. For multiple treatments, it starts having more problems because there's more problems with the estimation. There can be more noise. So what people came up with is they just find one model to estimate revenue and conversion together. So either you use your favorite linear regression, your deep learning or not deep learning model with 2 outcomes, or now XGBoost with 2 outcomes. So you choose your favorite thing and you do it. And where most research is focusing nowadays is how to do this end-to-end model. So people want to do estimation with optimization together in a way that instead of using the errors from the estimation, you just use the optimization problem and you propagate these errors back to your, usually a neural network. But what ends up happening in practice is that this end-to-end model usually has all the other terms. It just propagates through these terms. So you can imagine as a neural network, in the modeling part, you get these outcomes, you put it into a solvers, and people have developed some Lagrangian layers and stuff like this to solve Lagrangian problems, but you can find your favorite way of solving the problem. So the main issue here is that these solvers have to take, again, the problem of causal inference, right? We cannot predict what would have happened to someone if they had been treated. So you don't really have the outcome for the optimization. And when people have done it this end-to-end, they usually assume they have the costs, but a lot of times you don't have it. So you have to actually calculate a way of adding the ideas of averaging out to propagate this error back. I'll go now to constraint optimization with multiple treatments, but do you have any questions here? Feel free to ask. Yeah. Oh, no, don't go for it.
So I like the example of promotions, but for example, when I open the.com, I can also see have some hotels marked with promotion sign. So basically it suggests that you promote the promotions not only to users, but also to the hotels, right? So, and in this case, I can imagine that hotels may pay to booking.com some money and you will uplift them maybe in their ranking. And in this case, it is the treatment, like if you uplift one hotel, for example, it will affect everyone else, and the other hotel that was down with it would like to opt in for promotions as well, and there will be some sort of competition.
Yeah.
And I'm wondering, in this case, how do you estimate this causal, treatment effects, because you somehow need to model their competition.
Yeah.
So basically, in other words, it feels to me like in this case, whether somebody else gets a treatment does not affect me, right? But if you give promotions to hotels, whether hotel Hilton gets a treatment also affects me as well, right? So how would you do this?
No, that's actually a super interesting question, because we have actually, there's a blog post from a colleague that worked at Booking in our website that he actually tells of the approach of how you actually can measure this. So he made a thing that's called partial blackouts. No, partial blockouts, where you actually, instead of randomizing only, let's say, users, you actually randomize in two axes. You can randomize both users and hotels, not all at the same time, but it's like 5% of the users see 5% of the things, or they don't see 5% of the things. And then through this gap, you can actually measure what's the impact of someone being in this campaign, of not being in this campaign from the hotel side and from the user side. Yeah, it's super cool to actually check. More questions? Oh, go for it.
In the uplifted modeling part, if we have a user population of say Booking, right? So like, I actually use Booking to book my hotel for this conference, and I had to book a hotel for this conference, right? Because I was going to go to the conference event. So, I would have booked a hotel no matter what, right? Even if the prices were extremely exorbitant across the board, just because I knew the place to sleep. Is there some amount in this uplift modeling trying to factor in like people who they're going to do it no matter what, right? So you may not necessarily offer them a discount because this person is going to make a book versus some like, oh, these people are on the fence, and that discount might actually move them, right? Because in the first case, that would actually probably hurt your revenue if you offered a discount to somebody who's going to do it no matter what. Versus if somebody who's on the fence, maybe that can decrease by spending your budget. You converted them. I don't know if I'm using the right terms here, but does that make any sense?
Yeah, no, it makes total sense. And I think there's several perspectives to what you are saying. For example, it depends really, and this is a problem that I think a lot of companies have to think when they do things, is when you are optimizing things, what you optimize, you are really focusing on that. So if you use something like lifetime value of a customer, it's like, I would like you to use the platform, right? So in that sense, giving you a promotion now, even if you book anyway, could be the right decision, right? From a conversion perspective, it could be the wrong decision. But also you can think that, you know, there's different hotels and you can do two higher or lower hotels. And there's also the legal background of this, all this, right? That we don't also want to purely target people based on this, and we don't want to discriminate. So things are not also done to such a granular level that sometimes people think that they are done. They are done at a more superficial level, a more clustered level that doesn't take much features, personalized features into account, because it's not proper, and we don't want to have also completely that behavior, right? So I mean, there's different levels there. So it's how you focus to optimize. There's the legal and the ethical behavior you want to have towards the customer. And yeah, so there's a lot of perspectives into it that you have to take into account.
Follow-up question to the lifetime value of the customer.
Yeah.
How would you see how a treatment affects lifetime value? Would that be like a very long experiment?
So I mean, it is a long experiment, and that's why usually it's harder to measure, I would say, lifetime value of a customer. A lot of companies then use models, and these errors can propagate because you're already using a model to estimate what would have been the lifetime value of this person, right? So that's why a lot of times you have to use something intermediate, something that you find like as a proxy that represents well something between right now and the long-term idea, something that represents that gap. I mean, I honestly, Yeah, so I'm not deeply inside into the team that uses those kind of things. There's a lot of literature, and a lot of companies have tried to actually estimate properly. It's a hard problem because you are trying to say, I mean, lifetime value is not the whole life. It's like you say like 1 year. And so you have to look into the past and imagine what are the characteristics that make someone stay in the next year in your platform. But yeah, so it's a very involved problem that honestly doesn't have a very easy solution. Yeah. And active. Oh.
I remember all the facts and that's that value should be positive. So if that's negative, we need to do something else.
The weight is sorry, I was thinking of a neural network suddenly, and yeah. So if I go back, sorry. So in this area, you're saying?
So here we see the weight.
Yeah.
A negative value.
Yeah.
And I remember mostly the net set problem will take the positive value for the line.
Yeah. So there's actually a cool work done by the colleagues that actually have authored this presentation in the past. And the thing is that, yeah, most of the times it's defined for the positive case, and they actually extended it to the negative case by this visualization of the graph, so the visualization in the axis. And the main idea is that, okay, so the backpack has a limited weight that it can handle, which is B. And if you are making profits, so if you are in the green area, the intuition is actually quite similar. It's just you are creating space in the backpack. Your negative weight is a backpack that is bigger. So the backpack has a space B. As soon as you are something with a positive revenue in this green area, what it means is that the backpack just grows a little bit in space. So this is the intuition between, I mean, if you're still thinking of a backpack. So it's like, if you want to stay in a budget 0, it means that you could, if you have a lot of this green area, these green points, you can go more into the yellow area. So maybe customers that is not the best investments now, but because you are at a break-even budget, you can say, oh, I can go there. But this depends from more an economics perspective, if you want to optimize it from a marginal perspective or from an average perspective, which all, philosophical discussions.
What's the number of how many users are you solving this optimization problem? Is there some kind of complexity which limits how many split this budget into? You mentioned clustering before.
Yeah, we say clustering from a level of like characteristics, right? So we only use granular characteristics that don't go into details of who is this person, etc., etc. So that's also like more a constraint we have as a business, to not go into details on really saying for this exact person, dude.
With this eye, how many eyes are there when you're solving this problem?
How many eyes? Eyes you can have a lot, right? We have a lot of active monthly users, daily users, millions. So you can do that based on that, right? But the X doesn't allow you to go deeper, right? If your features don't allow you to go deeper, then you can have 100 million and it just doesn't matter.
So the algorithm that you present is linear, that the one that solved the backpack problem. So that's scale I to a million.
Yeah, you can scale it very easily if you do the sorting, yeah. There's just one issue when you go to, for one treatment, it's very easy. It scales very easily, linearly. For the multiple treatments, there's one caveat there, yeah. Oh yeah, sorry. I just wanted to talk for a specific work that actually was done at Booking that was actually quite cool, because I wouldn't say it's very technically deep, but the thing is that it's a really cool hack, in a sense, in practice, to actually solve this problem in a nice way. So if we are in this scenario that we only have conversions, we have only conversions have costs and revenue, it means that our matrix is like this. So when persons don't convert, so they don't buy anything, we don't have any costs, we also don't have any revenue. And I'm a little bit abusing here by saying that there's no treatment effect information there, because there is, because it helps to make the average of that case. But all of these cases are just zero. They don't count in terms of conversions or of revenue for the optimization problem. So if you sum up the revenue of all the cases in treatment, including the zeros, the converted, the non-converted or not, adds to the same sum. So in the end, you end up having the same revenue, taking or not. So if we are in this scenario where you have the value and the weight, so you have the K2 of conversion divided by the K2 of revenue, you can just use the Bayes theorem if you are in a randomized trial. And the thing that is quite cool here is that, so the denominator here is the probability of someone choosing treatment or control. And because we're in a randomized trial, this is a fixed number. If it's 50-50% that are divided, this number is going to be 0.5. The last term in the numerator, the probability of booking given X, doesn't depend on the treatment. So if it's going to appear in the value and in the weight terms, it's going to cut. So we don't have to take that into account. And then in the end, we just end up with this term here, which is the probability of treatment given converted. And this actually sounds super weird, honestly, what you are doing here. But the idea is, if you imagine that, for example, some characteristics and features in the control group make 10 bookings, right? And the same characteristics in the treatment make 15 bookings. What this means is that in the end, you have a 5 difference, right? So you have more people that end up making conversions in the treatment than in the control group. And that already represents an increment. So with this, you only need this term, this S, we call it S here. And we have these A and B terms that are just a fact of converted revenue in treatment and control. So if you are under a coupon personalization, actually these A and B terms are constant. So if you're just giving a discount, like a car discount, you can even assume that these A and B terms are constant. In other scenarios, you still have to compute the revenue of the converted and the revenue of the control. And just to say that one of the curves we sometimes use for this analysis, extra curve. So besides looking at the value we're doing in conversion and the value in revenue, we sometimes look at the return of investment curve. In this example, I'm just trying to show return of investment is just revenue divided by cost, or uplift in revenue divided by uplift in cost. And you can just see, compared with the previous curves I showed, that there's this area. This doesn't say us anything about booking rates, right? This is just says how much money is being spent in this case. So we're just showing that the green area, some revenue, extra revenue is being made. So the curve goes up. You go smoothly down, and there's this area where conversions are positive. So it's the yellow area. And at one point, you go into the red area that you neither make revenue nor conversions. You're just hurting yourself by doing this. A lot of times you can stop at one. That's a really efficient campaign, but it really depends on the objectives you want. Yeah.
May I ask why the head section starts like that? I expected to perhaps start from where the lines intersect, perhaps.
Where the lines intersect.
Or like, yeah, where the RI curve hits one or something. Like, why is it over there?
Because you sorted based on revenue, right? So if you are making money, the first persons actually you have less costs than you have of revenue. because you are making. So then you are going to be above 1.
No, I mean, actually, is there any significance to like the point where the red section starts?
Yeah, the significance here is like, so in this case, you don't see it, but I'm just saying this is a curve we use more for a diagnosis case. And the red curve here, the red area, I was just saying that this is an area, for example, that you would have on the previous graphs, you could have negative conversion. So it's just the revenue is going down, and at this point you already entered the red area that you have negative conversion and you already had the negative revenue. So it doesn't have significance here because the curve looks the same, but it has in the conversion area. I was just adding this graph as extra diagnosis we can use for looking at models. Any more questions on this area? Okay, constrained uplift model for multiple treatments. So what I just wanted to say is that, so for multiple treatments, you can imagine that you can either give multiple discounts or it can give just disparate things that actually have nothing into account. So in one, you compare a page, you compare with sending an email, with giving a discount, what's the best option? And so you have this CATE, so this average treatment effect, and this gives you, you can do the same thing, you just have more treatments here. So this is the same thing, except you just have more treatments that you are comparing. Again, the solution to this problem is called knapsack, but this case is the multiple choice. So everyone has different items that they can choose from, and they will always have one item. And again, they have a value and the weights, and these different items are just different treatments. And you can just select the ones that have a better ratio. But the interpretation is slightly harder in this case. So I'll just go over the intuition and I'll kind of keep a little bit of the mathematics apart. So you're trying to see the cases where your budget is the treatments you are giving are the best for the budget you have. So again, our friends, this beautiful graph, that you have the positive, the ones where you have the yellow area where all the action happens, and the red area where you don't want to be. So if Bob comes again and he has like 5 treatments where 0 is the control group, it's 0, 0, right? Because giving the same as it was before, the uplift is going to be 0. And he has a treatment 1 that is great. So you always make money and you get some extra conversions. So to solve this, if you only had Bob here, is you would do a Pareto front. And why would you do a Pareto front? So you never want to give the control in this case, because it always is better to give 1, because you always make money and you always make more conversions in 1. So it never makes sense to give the control. But then for the case of the treatment 2 is a little bit more questionable. In the case of Bob, it's harder to think about it, but if you are in a big company, you have a lot of people coming. So it's not Bob, it's a lot of people with those characteristics. So the idea here is that there's always a linear combination between treatment 1 and treatment 3 that is always better than treatment 2. So if I give 50% of 1 and 50% of 3, is always going to be better than just giving treatment 2. So treatment 2 is not efficient in terms of its optimal conditions. And if I progress, I can just calculate these slopes, and these slopes can be interpreted as a marginal gain. So it means if I'm at treatment 1, how much extra value per weight do I gain by doing this? And they're always monotonically decreasing because we are in a Pareto front. By definition, they always have to be slower slopes because of the way it's constructed. And the crucial point here that they actually developed in this paper and that you asked before about the negative revenue is that the crucial point of this solution is how do you estimate the marginal gain of the first point? Because as the knapsack is originally only defined for the positive weights, with the negative, I mean, you just give it like a negative slope in this sense, and it always preferred in this case because you always make it. It's always preferred over control. But you can go for the details. So in this case, if you'd have Bob and Amy, how would we select giving treatments to them if I would start from now, from the budget, the minimum budget possible, that would grow my budget. So if you have to give a treatment to them anyway, so we'd always give to Bob is treatment 1 and to Amy the control group. And then you say, oh, I want to be a little bit more, send a little bit more of my budget. What would I do is I would focus on giving it first to Amy because it's the most marginal efficient. So it has the biggest gain, biggest value per weight slope. So I would progress here to Amy with the budget. So if I increase my budget a little bit, I would go with Bob because he has, again, the best marginal efficiency there. And again, I go for Amy, and then I go for Bob. And this is how you would progress in your budget. This is the idea. So again, you can sort by the marginal gain over the Pareto front. I know this is getting a lot of terms now. And in this case, you actually would have multiple people with this in this curve. They would be repeated because you would have them for each treatment in this curve, but then you just decide to give which you give them the last treatment possible. So in the beginning, you would give to Bob just first treatment. But if I stop later, I give to Bob the second or third treatment in the Pareto front. So you only care about treatments in the Pareto front for each individual. And to answer your question, that's why the algorithm takes a little bit more time, is because you would have to compute the Pareto front for each individual. But there's a lot of people that have assumed that because you are in a revenue and cost scenario or in another scenario that they optimized for, that you have the marginal diminishing returns, the assumption in economics, and that's in that sense, you always have a Pareto front anyway, so they ignore that part completely. So they say, I don't make a Pareto front. But the last work of Susan Atty, she actually looks into doing a Pareto front too for the knapsack formulation with the budgets. How to solve this? The same way, but it just gets a little bit more complicated because the errors propagate a little bit more. And just wanted to recap what we talked about, which was long in this 40 minutes. So thank you for standing here and listening to all these knapsacks. So the first was treatment personalization long ago, where it didn't have a cost. So you just give the one that is the highest. Under budget constraints, you can do a knapsack formulation, and it's simpler. You just divide the value by weight with one treatment. You sort by that, you solve it. And the last one is the multiple treatments with personalization under budget. So with this, I finished this part. I would ask if you have questions, but I think we ran a little bit on time. So if you have questions, you can ask. Don't feel pressed. She just gave us completely freedom. Okay. So.
Okay, my name is Anastasia. I am a machine learning scientist at Booking, and I have been with Booking for 5 years. I spent 3 years in accommodation business unit where I was focusing on improving guest experience. And now I'm already have been for 2 years in marketing. So yeah, and we are moving to the application part. So for now, maybe I will recap slightly some things which Hugo and Philippe already covered, but it will be from a different perspective, like how to apply it in some practical use cases. And also, if you have any question, don't hesitate to ask. So again, probably you remember treatment personalization. Why it is important? Because, well, not all kind of personalization are relevant for all users. So let's think we would like to, at Booking, to improve family experience, yeah? And you can say, okay, we are young, we have no children, why do we even need it, right? So basically, we can clearly say that we have some group of users, like families, who can be very interested in that kind of experience. And we have a group like of young people who maybe would find Legoland or Disneyland very entertaining, but mostly it's not something which is interesting to them. And usually we are talking that this kind of personalization have, that kind of treatment have no cost or only operational cost, but in a long-term perspective, if you are not receiving relevant content, it can actually harm your long-term value from our perspective. So let's return to family-friendly experience. So how we can solve it? We can divide all our listings into two big groups, like properties which offer some family-friendly facilities, amenities, attractions, and the rest. And we can divide our users into two groups, and we can derive is this user interest in that kind of treatment based on the search result. For example, it's a simplest variant when we define how many adults and how many children will be traveling, or we can build a little bit more complex model, because yeah, it can really, because maybe you are still interested in Legoland experience. And for that users, we can offer two different kinds of treatments. And well, if it is done right, we should expect to see some positive uplift, let's say in conversion or in revenue, depends what we are interested in. But yeah, actually we have millions of visitors and 28 million of listings on our site. So that dimension, like family friendly, not family friendly, is only one of them. And our users have the ability to narrow their choice. So for example, if you are traveling to Birmingham, you can use a set of filters to define basically things which you are looking for. It can be distance from the center of Birmingham, it can be fun things to do, or maybe you would like to have your pet with you, right? And our colleagues at Booking worked on finding the best, the most suitable set of filters for you. So in that case, set of filters is a treatment, is a personalized treatment. Another example of treatment personalization is optimizing UI elements. It also was done by our colleagues at Booking, and they were working on optimizing three main different categories. So it was a property type block. So if someone, so yeah, you mentioned that you were using Booking to find the accommodation. So basically property page has a set of different blocks. They can be optimized. Landing page can be optimized. And also banners in the search results can be optimized. And there are a few different sets of banners. So this one, okay, I will show you. This one is more informative one. So it's just explaining what some features means. Another type is providing you some recommendations. So for example, what to do in Birmingham. And there is a third type of banners, which actually have triggered costs, which Hugo already mentioned. So basically this cost, it's not like, so we are not paying anything for, not paying to someone, because if we, let's say, showing ads at some, I don't know, social media, in that case, we should pay for that impression, right? If we show that on our site, we do not pay for showing that, but actually we would like, well, taxi drivers to be fairly compensated, right? So they should get their money. And for users, we would like to offer that kind of experience that if they book accommodation, they can have a free taxi from the airport. But also, maybe not all users are interested in that, because you can think about people who are traveling by car. If they will see that kind of banner, they can find it is like, well, not relevant for them at all. And yeah, how to deal with that type of problem, it was like just covered by Hugo. And it is from the paper Retrospective Uplift Modeling for Dynamic Promotion under ROI Constraint. So is that knapsack problem and all the things which was just covered. And of course, we have a lot of different things. So we have accommodations, we have car rentals, we have taxi, flights, attractions, and of course it can be offered in a different ways. And also it's very common for different industries. So for example, like some telecom providers, they tend to bundle together like TV and internet and offer something like buy two, pay for one. Another interesting paper which we would like to mention is how to deal with that multi-treatment personalization when you have many different variants, what to offer, plus you have ROI constraints. So basically you need to find the best offer for each user, right? And be mindful about cost. And in that paper from Amazon, they are offering very interesting solution for that. So they were using mean cost flow network optimization. And it's very similar to, let's say, if you should deliver some goods and you have a different variant, like of your logistic routes. So the idea here is to find how to find the cheapest route. And also they are not just address that multi-treatment personalization, but also there is another thing about optimal budget per every offer. And it brings us to the next, like quite big chunk of applications. It's like one of the main applications in marketing, I would say, how to do optimal budget allocation. Because like in almost, I believe I can say in every country, in every company, which are doing some marketing activities. So basically there are some strategic business goals, what we want to optimize. For example, we can try to get more new customers or improve retention or make more revenue, whatever, right? It's defined by business. We have some budget for that marketing activities, and usually we also have constraints. So basically we can spend some fixed amount of budget, or we can spend some amount of budget with the condition that our ROI will be greater than something. And market segmentation can be also defined by business. So it can be some, I don't know, some markets, let's say Europe, North America, Asia, or it can be done by interest, by user lifetime value, or by some clustering techniques, right? There are plenty of things. So if we talk about solving optimal budget allocation, it's, well, super popular. And usually one of the problems that if you have that market segmentation, you have historical data, you know what you want to achieve. So basically you can measure or predict market response. The tricky part is how to match that predicted response for every market with budget allocation. So there is a nice paper. Well, I believe Hugo also cited it. Yeah, so basically what interesting thing here is basically the treatment personalization and budgeting problem. They are not mutually exclusive. They are going hand in hand. So you have a lot of literature which address like one problem, another problem, both problems together. So in that paper about called Unified Framework for Marketing Budget Allocation, they are basically addressing that issue that getting market response, that's one thing, that's one problem, and applying budget allocation in an optimal way on the top of it, that's another problem. So they're offering a solution for that. And of course, you should like test your solution online, because if you build something on a historical data, maybe it would not be valid in a month, a day, whatever. It depends on the problem. But actually, if we think about that framework, we have budget allocation, we have treatment. It can be like multiple treatments which we want to optimize. And also another important piece here that we also have a different channels. It can be or for example, we can, that kind of promotion, we can show them on our site. We can send email, we can send physical letters, we can start some advertisement in social media, and every channel has a different cost. So optimizing channels, treatment, and budget allocation, it's like the main three pieces from the application point of view. So a lot of literature basically offering you optimization of at least one of that problems. And one more work which you would like to mention here, which basically solving two problems. It is about uplift modeling for multiple treatment with cost optimization. And why it is interesting, because maybe you remember X-learner and R-learner. So the authors of that paper, they introduced modified version, so-called net value X-learner and net value X-learner, which take into account the different kind of cost for every channel. And as Hugo said, so in theory, predict optimizing for conversion and optimizing for revenue should be the same, but in practice, because if you are dealing with cost, you have a continuous variable which is skewed. So according to the results of that authors, this version provided better results than, for example, two models approach. And the next topic which we have is implementation challenges, because, well, you can find a nice paper which describe very nicely techniques which you can apply. And if you're trying to apply it in practice, you can meet some surprises. So the first one is uncertainty. So basically, yes, you can follow some literature, find that nice line, find that fine intersection, and it can look super good on your historical data. But if, for example, you apply real-time traffic, you can see, and you will measure the potential uncertainty, it can be harder to decide which percentage of population you should treat. And there are two ways, basically, how to deal with that kind of uncertainty. So one way is you can try to make your model more robust and decrease that uncertainty. And in the paper to treat or not to treat, authors propose like ensembling techniques plus some cross-validation to reduce the uncertainty. And another approach is basically to, like, more from a practical point of view, if you know that, okay, that constraints met in 70 or 80% of time, that you can just make your decision taking that uncertainty into account. So basically you are not reducing the uncertainty, but you make more informed decision. The next surprise, which you can see, is that, again, your model is like pretty nice. You put it into some production settings, and after that, due to the drift, and there are two types of drift. One type of drift is basically when your target and your features do not have the same relationship as they had before, or like even the meaning of your label is a different one. I would say it's very popular in a fashion trends. So if you define something as a like fashion item, it can be true for today, but maybe in a year it's not true. And another type of drift is a feature drift. So basically when the distribution of your features is changed. A very good example here, I think, sanitizers and face masks during the recent years, because like 8 years ago, no one would propose that, I would say. And at some point it was a huge boost, and now it is like slightly declining. And well, what you can do to avoid but not avoid. So basically, drift is not that something you can avoid. So basically, you are interested in detecting that and mitigating that and adapting to it, because yeah, how you can avoid that thing. So basically, your optimal line just shifted, right? And what you can do, so first of all, you can set up monitoring for your features, for your predictions, and measure the difference in distribution. And if this difference is like too big, you can get some alerting. You can regularly retrain your model. You can do some regular evaluation, like, okay, is it still true? Or you can introduce feedback loops and try to adjust the prediction of your model dynamically. So in that paper, which we already mentioned a couple of times, this about retrospective estimation, it also was addressed. And the authors proposed to dynamically calibrate the output, and according to the experiment results, it was more beneficial than just use unmodified prediction. So you can say, okay, we have models, but we would like to explore, because maybe, so here we talk about drift, but it can be that some new factors came into account, which you never even counted for. And overall, the development process can look like, well, at step 0, you have no uplift modeling. So you have no treatment and treatment. You build your uplift modeling and you go to the step 1. What's important here is that from a practical point of view, even that step 0 and correctly measuring the uplift can be a little bit tricky. So for example, in a social media advertisement. So for example, if you have some providers like, let's say YouTube, which offer advertisers a possibility to play the ad, there is an action happening. So basically all advertisers are competing for some place and for users. So randomization of users to measure the incrementality effect can be a way trickier. And there are a few different methodology how to measure it more precise. So here I would recommend that ghost ads. The idea here is basically you are not do simply randomization, but control group, it is a users who would have seen the ad. So basically they should be selected to be seen the ad finally. But if they are in control group, they will never do that. And in your test group, this user who seen that. So it's a quite interesting paper, so I would recommend to read it. And yeah, what is happening after you build your uplift modeling? So at step 1, you can test it in the A/B setting. So you have no treatment, you have treatment, and you have selective treatment, right? And at some point you can say, okay, I would like to build a better model and go to step 2, where your selective model can be different. But you can say, okay, maybe we've already talked about uncertainty. Sometimes it's not even clear, like where should be, like what should be your selective. Maybe you have not one candidate to test, but maybe you have many. The problem is if you want to test it in the same experiment, you can run multiple variants, of course, but in that case, you should run your experiment for longer, for example, because it can be power issues. So our colleagues at Booking also address that thing, and this paper was published 2 years ago at NAIRIPS, and they were addressing the problem, how to basically make that decision quicker, which variant is better. Another interesting problem, if you develop a new model, sometimes it's like also hard to, let's say you have model where you address the drift problem. So technically speaking, you have the same features, you are predicting the same result. So only some subset of the output changed. So how to correctly measure the impact of the new model and say that the new model is better than the other one. So the whole experiment design can be done differently. So for example, you can treat only users for which you get a different prediction. So if you are getting the same prediction from both models, you can ignore them because you are measuring the effect of your new model. Unfortunately, this setup, when you have like every time you test your changes in A/B setup, okay, there are more variants, so it's more like ABN setup, but let's call AB. So the few main flows here is, first of all, this costly exploration, because you always should have a control group which are not exposed to anything, right? Or if you made the wrong decision, also a lot of users will be exposed to that. Usually you're dealing with static models. It can be treatment leakage. It depends on the your randomization. And also if you have some long-term effects, let's say, so there are two things. So there is a seasonality effects and long-term effects. And it depends like how often you are training your model, because it can be that, I don't know, during the winter, all users are interested in going to some ski resort. And during the summer, everybody wants to have a beach holidays. And you can capture something which is not relevant, or like the whole industry is moving into some direction which is changing. So yes, of course, if you see that costly exploration, you can say, okay, I would like to have constant exploration with a smaller group of users. And in that case, of course, you can think about bandage-based models. If you think about some classical examples like greedy, USB, UBC, yeah, it's the end of the day. I'm mixing letters. Or like Thompson sampling, in that case, you can ask, okay, we can do exploration. It sounds good for optimizing conversion, for example. But what to do if I have a limited budget, if I have cost involved, right? So there is like a whole set of work. It's also, as you can see, leverage knapsack problem. Well, I would say it can be a separate tutorial for that type of thing. So basically, if you are interested in the topic and cost is important for you and you would like to have a constant exploration, please check that sources. They should be very useful. And another issue which you have here, so previously it was like you were slowly retraining your models, releasing like at some cadence, but now you're doing constant exploration, which leads to another problem, right? Some users can be like overexposed to all the changes. And well, what you can do, of course, you can check, was this user already exposed to some solution or not? Of course, here you have a trade-off, because if user already was exposed to some treatment, you can still show the same treatment to that user, but that means that, well, exploration is done a little bit differently now, right? So it's also addressed in that paper. If you're interested in details, please check. And here, yeah, we are moving to a very interesting topic, which we would like to have at the end of that tutorial. It's about responsible AI and main principles. So overall, like different companies have a different formulation of responsible AI principles, but mainly all of them include the same topics like ethical, fairness, transparency, and privacy, right? So about ethical things, so at the beginning, Felipe mentioned that, for example, when COVID vaccine was released, it was, well, from a scientific purposes, maybe you are interested to measure the effect on the older people. But from the ethical perspective, you should save their life, right? So if you are developing something, it's a trade-off, right? So basically you should follow that ethical principles. Another thing is fairness. So basically if you're creating some solution which potentially can discriminate users, and the primary things like red flags is age, gender, maybe location. And here, please be aware that in that case, it means that you cannot use some features because you can say, okay, I would like to make a really good personalization. So if I would know more about my users, and indeed age and gender can provide better personalization, you cannot use it from a fairness perspective. Even if you remove only that features, it still can be a set of things which are correlated with that. So sometimes it's, well, we will suggest a method how to check for it. And another thing is privacy. Again, you can say, I would like to get as much information about my users as possible. And maybe you have a good intention. Maybe you just would like to offer them like just a good experience. But there are like even legal things, which I believe everybody already had about that. It's GDPR and CCPA, which are regulated things. So the main idea is like you should not collect information which is not relevant for that task. And also there is a set of features, like for example, some PIA information, PIA features. PIA in that case means that some person can be identified. So if you have emails, address, names, well, also please avoid. Yeah, or you can always consult with the documents. And that thing about if, let's say, you would like to develop some Uplift model, you say, okay, I've excluded age and gender. You are not sure, maybe there are other features which are correlate with that. So basically how you can even check that you do not create any issues from the fairness perspective. So there is a set of techniques which provide, it's called ML explainability, and the idea is basically by providing explanation for your model, you can address that bias and discrimination, potentially, at least have some insights. You also do error correction and improvements, because sometimes you develop a model, especially if it is a black box model, you can just deal with a ML metrics like accuracy, F1 score, whatever. Then it can be some issues inside. And also you can provide better user experience. So in some cases, it also can be your personalized treatment. And you can improve trust and user confidence. So basically we did that, we provided that user tailored explanation for property owners and tested that in the experiment, and we found indeed that it was beneficial for trust and user confidence. And if you're talking about better user experience, there is a paper from Spotify, Explore, Exploit, and Explain. So basically they not only provided song recommendations, but also provided explanations, and they also found it more beneficial for user experience. And of course, yeah, regulatory compliance is important here. So how to achieve it? Well, first of all, we can divide all methods into two bigger groups. Like there are methods which can explain every single decision. So for example, if someone was applying for a mortgage and didn't get it, this decision can be explained. Yeah, if it was obtained with a machine learning model. Another way of explanation is explaining the whole data set. So for example, again, if we took that mortgages example, it can be like users with a full-time job and PhD tend to get mortgage more often than the other types of users. And if you think that explainability is important for your task, you of course can start with the explainable models, which are decision trees, decision rules, GLMs, even nearest neighbors, right? Because you can say, okay, these people were similar to you and they did that. The one small caveat here is basically if you have tree like that one, it's still explainable. But if you have a tree with a depth of 200, it is not very easy to explain that. So please also can take that into account. And there is often in the literature, you can see that so-called trade-off between explainability and accuracy, which is stating that that inherently explainable models have not so good accuracy. So, and if you have more black box model, you can achieve better accuracy, but well, they're not explainable anymore. And to address that, there are some methods which can be done on the top of your black box model called shape. Well, it's like a different variation of shapely values implementation. It can be partial dependence plot. It can be surrogate models. But there is also researchers who are saying that if you would put enough efforts into feature engineering and like learning all key features about your domain, it can be that this explainable model gives you like still awesome, well, not less accuracy than black box model and still explainable. So in this paper, like stop explaining black box machine learning, yeah, the authors is talking about this. So let me check the time. Okay. I'm very briefly will cover 3 main methods which can be useful for you. So one of them, and I put it fast because people usually go directly to the shapely value things and do not use partial dependence plot. And this method was proposed by Friedman, and it gives a nice visual insights about relationship between 1 or 2 features and the target. So technically speaking, it is for every value in the feature you are interested in, you can get a mean response of your model. And for example, if you have, now I'm thinking about good continuous features, which is not age, but okay, let's have age. If you have age and income, and let's say for age, you are predicting the income, so you would expect to have something like that. And if you have some different form, like for example, opposite one, like people in their 16s getting like much more than people in 40s, that means that something can be wrong with your model, right? Most probably. The next one, I believe, is a super popular topic. So I would expect, so do we have people who don't know what it is about? Okay. I will cover it quickly. I believe everybody do, but so basically shapely values. This conception was proposed in game theory in 50s. And the whole task was how to divide payoff between players in some game in a fair way. And yes, it was introduced in 50s. It has very nice mathematical formulation. The main problem, it is computationally heavy. But some time ago, this problem was solved. And now we have like one very popular, mainly because it is open source, I would say, framework SHAP, shapely additive explanation, which is based on shapely values. And it provides faster computations, specifically for some model-specific models. For example, for tree SHAP, it calculates exact shapely values much faster than like original version. And it also can be applied, for example, for explaining the whole model and explaining each individual example. And another thing they offer is also sharp dependence plot, which is similar to the partial dependence plot. And we can move to the, Uplift, yeah, because basically now I was talking about explainability, but it was more in general case. So it's applicable for any machine learning model. But if we have Uplift models, do we have something specific here? So first of all, if we have like Uplift trees and causal trees, they are explainable by design, so you can just use it. If you have single model, there is a slight problem because basically treatment is one of the variable. So for example, if you use a partial dependence plot, you can use 2 features and have a grid. So basically for the feature of interest, you can have like that with the treatment and without the treatment. And if you have 2 models approach, well, in theory, you can have an explanation for every and just compare it visually. But there are more things which you can do. So maybe let's go into that example. So quick reminder that 2 models, you have 1 model for treated users, one model for untreated users. It can be any kind of model. So let's assume here that you have 2 black box models, right? And you can estimate the uplift as a difference between prediction of 2 of them. And let's say you have 2 features, x1 and x2, and you have that uplift. So if you have a partial dependence plot, this is a model agnostic method, which means that what you are interested in is basically the final prediction, which is uplift in your case. So you can have exactly the same thing as you do for classical ML model, and you can have a feature, and for every value, you can measure the average response from your model. Or you can do another thing. You can build so-called surrogate model. Surrogate model is, well, it is popular in a different application. One of the application is a distillation when you have like very complex model. So you can fit another simpler model, which will take into account inputs from your original model and prediction from your very complex trained model. Or you can do the same trick for explanations. So if you have, in that case, you have like 2 models, you can take the input because you have the same features, and you can predict your uplift. One of the variants, there is another method called inexplainability, called LIME. And the idea behind that method is to select an area and fit a linear regression. So if you have like very complex model, so you have a smaller region, fit a linear regression, and linear regression is an explainable method. So if you are interested in that method, you can read that paper with a cool name, Why Should I Trust You? And yes, so yeah, we are just in time, you see. If you want to implement something, maybe you should not reinvent the wheel. There are a lot of open source packages. My favorite one is the Causal ML, because this library is offering a lot of methods plus explainability on the top of it. And basically they offer that sharp values. And for two models approach, they're using that surrogate model trick. What is your favorite?
Causal.
Causal ML. And you?
I'd say for development, Causal ML is better because it's easy to change things because it's all written in Python. And CIKM, I think, is a little bit stronger in terms of having a little bit more thought through things, and it's by Microsoft and pairs very well with other packages like 2Y and everything. So that causal graph is econometric thing. So I'd say it's a little bit more mature from one side. It's not always easier to play around and shape their method.
Okay, so please check the rest of these packages. They are also good.
Right. Yes. Well, with this tutorial 3 hours long, we really hope that you guys took some learning from all these 3 goals that we had today here. These recordings are going to be available online, and also the reference, our contacts, so all that website we hope to keep there. And from us, we just want to say thank you for hearing us, and yeah, and hope you joined.